Okay, we'll get going because today we have a hot lunch and there are no hot plates and it'll get cold if we don't get there on time. And for that reason, the lunchtime bites are just being rearranged to start half an hour after the beginning of lunch. And if you could double the rate at which you take your food, then the queue won't be so long and it won't last so long. This session, I've been allowed Chairman's privilege to take 2 minutes to tell you that the British Crystallographic Association is actually hosting the European Crystallography meeting in Warwick this August. We won this in Istanbul in 2009. It hasn't been in the UK, the ECM, since 1977 when it was in Oxford. And so we're celebrating the 100th anniversary of the Braggs solving the first crystal structure in the UK by hosting this meeting. The meeting is shaping up very well. There'll be the usual keynote lectures and microsymposia, special Braggs symposium. We've got John Jenkin, the biographer of the Braggs, coming from Adelaide to give the first talk in the Braggs symposium. And there's some satellite meetings too. There's going to be some crystallographic films and a Bragg exhibition of some old equipment from the Royal Institution that the Braggs used. It's going to be held in the University of Warwick Arts Centre, which is a very nice modern venue with the necessary Costa coffees, etc. Around it, and a lot of breakout rooms that will be used for the SIG meetings and the council meetings of the various crystallographic associations. The local organising, here's the Braggs solving the structure, talking happily, and here is the organising committee locally and the it's going automatically. It's trying to hurry me up. The macromolecular crystallographers here are Vilmos Fulop, who's in Warwick, and we've also got Harry Powell on here for the computing, representing computing SIGs. And I'm also involved with the organisation, as you can probably see. For the SIG representatives, Keith Wilson is the person to talk to about microsymposia, and he's heading up the macromolecular European decision. It is going automatically, it's very good. The registration... Sorry, the registration costs we've kept amazingly low. Warwick guaranteed the accommodation in 2009 and have kept the costs fixed. The early bird, I think, will end on the 1st of May. The student rate is only £200 for the 4.5 days. So we've really worked very hard to keep the costs down. And the accommodation is going to be £30 bed and breakfast for students. And then there's, if you want a bathroom and running water and power, it's £42 a night. And then there is also a hotel on the site if you want all the facilities. And it's a very convenient site. They're all within 10 minutes walk of the actual venue of the conference. There's going to be a trip to Diamond, which is available for the last day of the sort of conference last day. So it would be great if you could all plan to come, bring your students, make it a really good showcase of UK crystallography, especially macromolecular crystallography, which is incredibly strong worldwide. And this is our chance to show it off, if you like, and also learn a lot of good science. Okay, so having abused my privilege, I will introduce Dr. Andrea Thorne, who was until recently working with George Sheldrick in Göttingen, but as of 3 days ago is with Randy Reed's group until in Cambridge until July, when she will move on to a Marie Curie and do her own thing a bit more. Is that right? So she's going to tell us about shell X-y and molecular replacement.
Is that working? Yes. So we have heard already plenty about molecular replacement, but to tell you about shell X-y and molecular replacement, the first question is possibly, what is shell X-y? I have to answer that before I can tell you about shell X-y and molecular replacement, obviously. So shell X-y is a program for density modification. It is very old. It is over 12 years already. It was originally designed for experimental phasing. Input phase information can also be an MR solution. I'll show you that later. And the current version can not only do density modification, but it can also iterate between auto-tracing the backbone of the protein structure and density modification. So it can improve MR solutions and identify correct ones. Just wait a moment. ShellXE uses the sphere of influence method for the density modification. So sphere of influence, to my knowledge, is the only program that uses it. Doesn't use a mask to exploit that there's a solvent region and a protein region. It uses a sphere of influence. So we take a point within our asymmetric unit, and we would like to know whether it belongs to the protein or it belongs to the solvent area, which is more disordered and has a flatter electron density. That is what is exploited by density modification. So we have that point, and we draw around it a sphere. The sphere has 2.42 angstrom radius, and that is the preferred one-free distance between atoms and proteins. We take that sphere and we plot the electron density on the sphere. So we look how much does it vary. If it is not varying very much, the electron density on the surface of the sphere, we flip the density because we believe we are not in a protein. If it is varying a lot, we sharpen the density because there's a certain chance that the point in the middle of the sphere refers to an atomic position, seeing other atoms at its surface. Hence, the electron density varies a lot. After a few cycles, this leads to the solvent areas being flattened and the protein areas being sharpened. Then, for the auto-tracing, we do a peak search in the electron density map we got from density modification. And we position either a 7-fragment helix, 7-residue helix fragment there, or one of 3 tripeptide fragments, whatever is fitting. Here, you can see the end of such a fragment, schematically drawn, of course. We extend this into the electron density at both ends by 2 amino acids. I only show one end here, and that are the 2 amino acid residues. They are alanine. We don't care about the sequence. Then we do a simplex optimization of the position of the residues by refining the 2 tau angles, determining where the rest of the amino acid is sitting, and the backbone torsions. After that, we delete the 3rd residue, and then we just move on as before, extending the chain until the electron density ends. Then we calculate a figure of merit. I'll explain on the next slide what the figure of merit is composed of. And then, if necessary, and if we have traced into another already existing trace, we splice them, so we cannot have overlying chains. The figure of merit for the chain is calculating using the density fit of the chain. Of course, it has to fit the electron density. Using the chain length, longer chains are generally better. The Ramachandran fit, because a good protein chain would fit the Ramachandran plot. Then we want phi and psi angles for consecutive residues to be very similar, because that means it's a good secondary structure. Within a beta sheet, you would expect phi and psi angles to be similar, and within a helix you would. And we look if there is a significant positive density, 2.9 angstrom from the nitrogen in the plane. So you have the plane with the nitrogen sitting on a triangle. You know, because you have placed your backbone, you look in the direction of the NH bond, 2.9 angstrom from there should be a hydrogen bond acceptor, so there should be electron density. All these go into the FOM, and from them we choose which traces we keep and which we don't. There's also another little trick in ShellXE, which is the free lunch algorithm. That is independent of the auto-tracing and can be used with or without it. What you do there is you expand your data with rough guesses for what you've measured. You are guessing, expanding your data. So actually, you didn't put in much. So it's like a free lunch. You get something for nothing, but it improves the density. Why is that so? So you correct for Fourier truncation errors, as 0 is a bad estimation for a not measured intensity. And also the phases, which at this point should be rather good, are the major influence. The intensities, if you remember cats and ducks, are not playing the main role. And free lunch is typically used only at relatively good resolutions from 2.0 angstrom. And it is particularly useful when autotracing is no option, for example, in a case with DNA, or if data are missing. So, for example, a whole slice of data is missing because your crystal got burned or because you didn't collect enough. Then free lunch is really very valuable. That is what it's looked like in a case where it really improved. So there was a slice missing from this data. Incomplete reflections were there to 1.3 angstrom. After expansion to 1 angstrom and filling up all the missing residues, missing intensities, we got this map. So it's very clear that you could better build in this map. So Shellix E and MR. The input phase information to Shellix E does not necessarily have to come from a substructure from some heavy atoms or anomalous scatterers. The input phase information can also come from a PDB. This PDB would have to be renamed to PDA as an ending. So you have done some molecular replacement. You would rename your PDB to PDA. You would have your data, you put both into Shellix E, and you will get out a PDB if you use the autotracing option. That's why it has to be renamed, so it's not overwritten. And a PHS file from which a map can be calculated easily in COOD. Shellix E can improve and correct MR solutions and establish hence a better basis for refinement. I'll show you some cases rather quickly where we observed what Shellix E does or doesn't. So, yeah, that's also the input. So to use Shellix E, you have to put it to your executable bin. It's only one file, and then you type Shellix E, name.pda, which should be renamed MR solution, and then you can put options, and that are switches which can be used for example, in Shellix E. So -Q is if you have helices. Otherwise, the helix fragment will not be used in autotracing. -S, the solvent content, is absolutely crucial for the density modification, so it should be as exact as you can estimate it. -A is the number of autotracing cycles. The option also will switch on the autotracing. -O prunes residues to optimize the CC in the beginning. This is a new experimental beta version option, which can improve the input MR model, but not necessarily has to. -Y is the cutoff resolution for the input phases from the MR model. So if you have a very small fragment, you think it's very correct, you would possibly take as much resolution as your data have here. But if you have a very big MR solution, you're not so sure it's correct, and there's a low homology. You possibly want to use -Y 1.8 or 2.0 or 2.2 or even 2.5. -E is using the free lunch, followed by the resolution you want to use. So the first case is RNase T2. We had a model with a sequence homology of 34%, that was RNase LE, and a resolution of 1.75, and space group was monoclinic. And the best TFZ I could get in phasor, using various models and various cutbacks, was 5.6. So, and that solution could not be refined in my hands. And that was very bad, because that was a de novo structure solution. We really wanted that structure. The secondary structure contained alpha helices and beta sheets. So I generated 43 MR solutions with rather not so good translation function Z scores in phasor. And then I used ShellXE with the option -Q. And that is the map I got out of Phaser. So you can possibly see why I could not refine it and not go on with this. And the LLG was 9, so it was not good either. And we really wondered why that is, because we had such a high homology model, and we thought the structure must be quite conserved. ShellXCC went to 28.5%. Everything over 25% is considered to be soft. And we free-launched the map to 1 angstrom, and what came out is shown here. So the structure has been expanded and looks better, but still it's a little blobby. So in the refinement of this showed that the bonds were systematically too long in comparison to the Eng and Huber restraints. So RefMec complained, and I used the what-if server and saw that the unit cell was too big. So the larger cell was the result of a wrong wavelength taken down at the synchrotron. It was just, the numbers were turned around, and that was used for integration. It was just one of those mistakes that happen at 5 o'clock in the morning at a synchrotron, and you wonder for weeks what has happened. The correct wavelength gave a better integration, 1.6 angstrom resolution, and immediately Phaser could solve it. But if it wouldn't have been for ShellXE, we possibly would have taken much longer to find out what was the problem. Because ShellXE placed one residue after another, it could compensate for the error much better, because of course it compensated a little here, and then with every residue it compensated the error. But it has also to be said that Phaser still tolerated the rather big error and gave a solution that could give a valuable starting phase information. I wrote to Robbie Houston, writing this up for my PhD thesis, because I just didn't want to go over the mistake I had made. I wanted to explain the whole story. And he stated in personal communication that 46% of the structures in PDB report had mostly minor discrepancies in the unit cell dimensions with regard to the ideal bond lengths. So wrong wavelengths, wrong detector distances, wrong unit cells seem to be a problem, and it could be compensated in that way, but I would rather think that, well, frame headers and so on should be looked at. Concanavalin A, 1.7 angstrom. I222 high symmetry space group, or relatively high, approximately the same thing. We generated Phaser solutions from homology structures with TFZ 8.8 to 4.1 for test purposes. That are all those 42 things. This is the -y cutoff in ShellXE. It does not play such a big role here, but what we can see is there's the Phaser TFZ. Here's the ShellXE CC. Remember that anything over 25% is soft. So what we could see is the good solution soft in ShellXE. Well, that's what we hope for. And then 2 soft from an intermediate range, but 1 soft with 3.8 TFZ. So one of the worst Phaser solutions still gave a good trace in ShellXE, and that seems to happen from time to time and will possibly be resolved with the new Phaser version. But from Phaser alone, you would possibly not believe it's a solution with the version we had at that time. So that is also for the same structure from one of the cases, the CC of partial structure against native data over 25% soft, and the mean phase error in respect to the final refined structure. And what you can see is the CC clearly indicates the moment the solution happens, somewhere in this region, while the mean phase error, yes, under 75 is perhaps soft, but it's not such a clear indication. And that was actually against what I expected. I thought the mean phase error would be a very good indication whether the structure is soft or not, but that wasn't the case. The CC actually proved the best indicator we had. Also, in a new structure, you would, of course, not be able to calculate the mean phase error. ShellXE can also be used for MRM pipelines, as has been discussed here several times already. It can be run with a single command line. That makes it very good for scripting. Auto tracing is, however, not feasible above 2.5 angstrom, but any structure that can be traced under 2.5 angstrom and exceeds CC partial structure against native data over 25% is solved. We called it the 2.5 angstrom 25% rule. But it has to be kept in mind that an MR solution that does not solve is not necessarily wrong. You should keep that in mind. If you think it could be a good solution, ShellXE cannot trace it, it's not a sign that this solution was wrong. It's only true the other way around. And that is used in Auto Rickshaw, Archimboldo, and in Ample. So that is an example from Ronan, taken from the Ample tests. It has a very long name, 1ZZK is what we call it. It was solved using the current, or the ShellXE version I had at hand done, 2012-6. And that is the phasor solution that led to the solution of the structure. So it's really, 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 really small. The TFZ was 2.5, possibly because it is so small. And ShellXE expands this fragment using the phase information from that fragment and the native data to this. So it gets to a CC of 32%, surely solved, and it has 86 residues, possibly because it traces from C alpha to C alpha. The end residues are wrong. What does this mean? The fragments can be very small if they are placed correctly, and that is exploited since some years in Archimboldo. Small generic helix fragments are placed with phasor, which is then run in a multi-solution approach. And then they run ShellXE. But Archimboldo is only feasible at resolutions of 2 angstrom or less reliably. And it performs better with helices because ShellXE is performing better with helices than with better sheets. So ShellXE can give you a quick indication of a correct MR solution. It needs no sequence, and hence it can be a step between MR and complete auto-building, as for example done with Upwarp. This is another example I got last minute from Ronan. That was the phasor solution they got in Ample. And that is the solution from ShellXE. So at first glance, they don't look very similar, phasor, ShellXE. But if you overlay them, it becomes apparent that the helix was just lying in a way that it had two asymmetric units, covered the helical content of two asymmetric units. And that was enough phase information for ShellXE to expand to the complete structure and to get a map to start refining. Again, the CC was clearly over 25%, being 29. Then I want to have a short dip into, there's also MRSAT possible because ShellXE is originally a program for experimental phasing. You can combine experimental phase information and MR phase information to give you more phasing power in case you need it. What you do there is you bootstrap the anomalous scatterer search, or even both the auto-tracing and anomalous scatterer search in ShellXE, if the experimental phases alone have proven to be insufficient for some reason. Also, model bias from the MR solution is, of course, removed. So you take the SAT data to ShellXE, which is preparing your files, and you get a file which is called name_fa.hkl. It contains the estimated alpha angles and anomalous differences, so your anomalous signal, more or less. And the native HKL both go into ShellXE together with a potential MR solution. And you go into ShellXE and you recycle as necessary. And in the same way as ShellXE is used here, the program Anode can also be used before ShellXE to generate a substructure which can be put into ShellXE instead of your MR solution directly. So what influences ShellXE runs? The resolution, the higher, the better. Shell XE autotracing runs not reliable at resolutions worse than 2.5 angstrom. In many cases, not even that. So the solvent content, the higher the better, but it has to be accurately given. That is the most important point for using Shell XE. The space group. We observed that triclinic and monoclinic space groups do often not solve as well as higher ones do, although the program applies anisotropic scaling. So we are really wondering why that is. Any potential answers to the question would be really welcome. Helical content. Pure beta sheet structures tend not to solve, or not at least to solve easily. The tripeptide does not seem to get such a good foothold as helical fragments do. So helical content is really an advantage if you're using Shell XE, and if you give the -Q option, it will run about 1/3 of time longer, but it won't do any harm if you don't have any helical content. And unfortunately, versions. So the performance of the program in respect to MR solutions varies with versions. And this seems to be a compiler-related problem. We dug deep into it as it was reported to us from Isabel from Archimboldo and from Ronan from Ample, and even I could see it. But we could not find what the exact reason is. We can only see that if we recompile older versions, we find they cannot solve it, and it solves certain structures anymore. But the new program can also solve one structure which has not been solvable before. So noting down the Shell XE version you used could be also a good measure, and letting us know, of course, what you observe. To sum it all up, Shell XE can prove useful in combination with molecular replacement to remove model bias by using the density modification. You remove your model bias, at least to a certain extent. To expand MR solutions, in particular if your density is not expanding outside of your search model, and to improve the density. To find correct MR solutions, to distinguish correct MR solutions from incorrect ones, in particular in pipelines. And Shell XE can also be used to combine experimental and MR phase information to give you more phasing power. Drawbacks are, besides from the version problem, good resolution is needed. So the autotracing option doesn't work at worse than 2.5 angstrom, and the CC is also not reliable. But you can always use Shell XE to get foothold of a substructure. So MRSAT could be done even at worse resolutions. If Shell XE does not work, the molecular replacement solution was not necessarily bad. That is to be kept in mind. It's only true that if your trace is working and your correlation coefficient goes over 25%, that means the molecular replacement solution gave you enough information, enough phase information to expand from this. The current beta test version is downloadable from the server. If you will find when you come to your home and you have a 2012 version that it has expired, because they all expired on the 31st of December because it's a beta test version, but you can just download the new one as you downloaded the old one. But this beta test version is a work in progress, and several things are upcoming for the final version. For example, parallelization. So currently it is only running on one processor, so you can start several jobs in parallel, but we want to have the whole program run in a multiprocessor style. So that's the end of my talk. I want to acknowledge my PhD supervisor, George Sheldrick, from whom you also under this email address can get password and registration information for Shell XE. Isabelle Usson, who taught me most I know about molecular replacement, Ronan Keegan and Jacqueline Bibby, who have supplied me with so many examples for this talk, Christian Große, Tim Grüne, and Navdeep Sio from our lab, Gabo Bunkosi, who also gave me some hints on phaser, and Robbie Hosten, who discussed with me the unit cell problem. I also want to announce shortly the joint ECA-IUCR crystallographic computing poster prize. The methods developers are going to have their own poster prize because it was always a little problematic that we didn't fit in a certain category that was given out. It will be for all posters presenting new developments in crystallographic software, be it GUIs or scripts or algorithms, and computing, including teaching and hardware automation and new usages for old programs and algorithms. It will be awarded for the first time at the ECM 2013 in Warwick, as Beth just announced, and the prize will be €250 sponsored by Olex. And that is a work in progress, but that might be the sticker you have to put to your poster to be eligible. So we hope we get some contributions at the ECM. And thank you for your attention.
Do we have questions for Andrea?
Hi, Mariana Biadana from Medical University of Innsbruck. I was just wondering, I have two questions about the resolution. First, why is it not working at lower resolution? I mean, 2.5 is not extremely high resolution, but in real life, most of the time we have to deal with 3 angstrom 2.5. And if you know if George is working on that, so if it's in his plan to try to get it working, the auto tracing also at lower resolution.
So the problem why it is not working at lower resolution is that the auto tracing algorithm with its simplex optimization and the FOM calculation using the hydrogen bonds is not working properly at lower resolution. The electron density just melts into one blob, which cannot be properly traced. That is why auto tracing is not working at lower resolution, and the algorithm we are using now will never be, at least according to George. I would think that if you have worse resolution, you should use a more sophisticated program that is also exploiting NCS, like Solve-Resolve or Buccaneer perhaps. And ShellXE is really for quick checks.
Another question?
Gábor Bungoczi from Cambridge. So I actually have a question to your first example, so the one with the wavelength ambiguity. And I'm just wondering whether were the crystals large enough to measure them on a home source so that you could have established the cell and avoided all these troubles?
Yes, they actually were measured first at the home source, but I didn't determine a cell then because at that, we were in a hurry. We were just freezing crystals.
Cooling.
But if would have
Cooling crystals.
Oh, sorry, you are so right. Why did it happen to me? No, we were cooling crystals, and of course the mistake is not a very intelligent one. Yeah, I just say that we just made a mistake that could have been avoided in many, many, many ways, but it happened, and we could not find a structural solution. And as I said, if it wouldn't have been for ShellXE, we would have possibly even taken longer finding out what the problem with this data set was. And my feeling is, while it's not a very common thing, it might happen to other persons occasionally.
Paul.
Paul Emsley, LMB. So I have a question for Commander Shepherd. The peptide tracing in COOT uses phi-psi refinement, and you mentioned the refinement of tau as well. That hadn't occurred to me. So could you expand on that for a couple of sentences?
It has been established by Gerd Grient, and what you do is you have the angle going to the side chain. So under the C alpha, and that angle can also vary. And we found that refining this angle, in addition to the 5 psi angles, gave really an advantage. So, yeah, I would try it. I would be interested in the outcome.
Okay, thank you very much, Andrea. Our next speaker is visiting us from Spain, Nicola Brescia. I'm probably not saying your surname completely Spanish way, all right, but from the Centre for Cooperative Research in Biosciences in Bilbao, which is where we've lost Pietro to as well for the year. And Nicola's going to tell us from lows to highs using low-resolution models to phase X-ray data with complementary techniques.
Thank you, Elspeth, for the nice introduction. And also, I would like to thank the organizers for inviting me and give this talk, which, as a title, has From Lows to High, using low-resolution models to phase X-ray data. And as you can grasp from the first slide, will be on various structural determination. Details of the talk, I wanted to underline the importance of structural virology in the development of methods. And before showing some other slides about that, I wanted to give you at a glance the timelines of the major achievement in structural virology, in electron microscopy, in X-ray, and in small angle X-ray scattering. And I want just to draw your attention on 3 milestones. These are all important milestones, but for the interest of this talk, I will just focus on a few of them. The first one is in 1963. There was this structure from brown mosaic virus that was obtained by Sachs and electron microscopy, and these were the early times of structural virology when complementary methods were used to validating each other's findings. The major step forward in combining methods was happening in 1986 when the group of Roger Burnett solved the structure of the major capsid protein of adenovirus, exon, and he modeled in a quasi-atomic model fashion this capsid protein into the EM images of adenovirus. Following that, the major, I think, point of inflection was in 2010 when the structure of adenovirus, is a large eukaryotic virus, was solved at 3.5 angstrom by electron microscopy and X-ray crystallography. And in addition to these 3 milestones, I wanted to also underline the first Sachs experiment done on a lipid-contained bacteriophage called PM2, which is actually the topic of my talk, and this was done by Steve Harrison in 1971. The only other X-ray crystal structure of a lipid-contained bacteriophage at very high resolution is the one from PRD1, which was solved in 2004, and it reached 4 angstrom resolution. Now, to underline the importance of structural virology and viruses in the development of molecular replacement phase extension techniques, I had the fortune 2 years ago to interview Roger Burnett, who is one of the fathers of structural virology. And if you bear with me, I would like to listen to an interview. 1 minute. This is
and so I sailed by ship to America on the original Queen Elizabeth, and then took a Greyhound bus from New York to West Lafayette, Indiana. And for the first 6 months I was in America, I thought I was in a movie myself because it seemed so strange and exotic. And Michael Rossman met me from the Greyhound bus and took me immediately to the darkroom to show me his latest diffraction photographs. And it turned out that he was very interested in using viruses as... really, he wasn't interested in viruses, I think, as such, but he was very interested in developing methods. There's a method called the molecular replacement method. And he was interested in viruses because there were many copies of the same protein in the same structure. And so he thought that was a good model for, or test bed for testing his methods, where you could use molecular replacement.
So I wanted just to list some of the seminal paper on molecular replacement techniques, and just to highlight what you do when you have a virus sample. You can have these three approaches. One, you can use electron microscopy. You have viruses have been a target from the beginning of structural biology because some of them were very easy to purify, to fractionate. So once you had the pure fraction from sucrose gradient purification, you could either go to electron microscopy, put on a grid, vitrify it, or look by negative stain, and then getting information in real space, do processing, and obtain a medium resolution reconstruction. Nowadays you can get atomic resolution. If you want to perform SACs, then you have your virus in solution. You record a scattering curve, which actually gives you a shape of the virus, the overall architecture. And if your prep is highly pure, then you can use X-ray crystallography. And usually viruses tend to crystallize. Sometimes they do not diffract very well, but you record diffraction images, and then you have to solve, as in protein crystallography, the phase problem. And some of these papers give you the guidelines on how to solve using low-resolution models to phase virus X-ray data. Now, the expertise that has been gathered on virus structural determination has been also exploited in some cases to solve the structure of small oligomeric protein. So use the use of cycling averaging, phase extension, has been also exploited in some cases. And here I put just a list of few references. The first one is particularly nice to me because this is a case where a small oligomeric protein was solved at 8 angstrom and then phase extended to 3 angstrom using a very similar protocol as used to solve the structure of foot and mouth disease virus by the Stewart group. Another interesting paper is the one from Samaras 9, where he was able to phase use a protein structure, but around 20 angstrom using an envelope from Sachs. Now, the bottom line of this is that in the past 3 decades, the multidisciplinary approach has moved from its original rationale, which was to validate the finding of each other techniques because they were emerging, towards the use of hybrid methods in predicting biological interactions and in uncovering dynamic processes and in bridging different resolution scales in molecular and cellular processes. Now, with that premise, I will enter in how we phase the PM2 lipid marine bacteriophage. Now, PM2 is the only member of the corticoviridae family, and it was the first lipid-containing bacteriophage to have been isolated. Now, before 1985, there were 400 publications on it, mainly because it contains a highly supercoiled genome, and the only structural information was the Sachs experiment done by Steve Harrison in 1971. The molecular weight is about 45 megadalton. It has a protein capsid here in light blue. It's composed by the protein P2, called P2. At the 5-fold, you have the spike protein, which is P1. And this protein capsid encloses a lipid bilayer, here schematically represented, and within the lipid bilayer, there is the highly supercoiled genome. So we crystallize PM2 using a similar technique as we use for PRD1, using vapor diffusion in capillary. There were some issues about stability of the virus, and the calcium was essential along the process of propagation of the virus and crystallization. And the most sad news, for me at least, was that 3 days after appearance, the crystals start to degrade. So we had to move fast from the time that we set up the Limbro to the time that we collect the data. So for some time, I had to run to our collaborators in Helsinki, set up with them the capillaries, run back to London and catch a flight towards Grenoble and collect the data over there. Diamond was not yet ready at the time, so the majority of these data were collected in ID 14.1 to ID 29, as well as the Swiss Life synchrotron. And these are the conditions that we use for the data collection. The space group was C2, and we had, for one crystal, we had 1 diffraction images. There was no way that we collect more than 2 images for crystals, so we had to screen several crystals. And the diffraction limit was about 7.5 at the beginning, and then we improved to 7 angstrom. So as soon as we gathered a sufficient number of images, we start to do some processing, and once we reach more or less 40% completeness of the data, we start to do the molecular replacement. We wanted to phase the structure. And in order to phase the PM2 X-ray data, what we used was a cryo-EM reconstruction of PM2 that was a low resolution. At the time, it was around 12, 13 angstrom. So what we did was, phaser is very automated, MoRep is very automated. What we did was a manual molecular replacement. So we know that we knew that we had one virus particle per asymmetric unit. We knew that we had an icosahedron. So what we did was calculate a self-rotation function to find the orientation of this icosahedron within the unit cell. And here I just depict the self-rotation for kappa 72 for the 5 folds. An icosahedron has 6 5-fold axes. Sorry, 6 5-fold axes, and you can see that these actually represent the facet of the icosahedron with the 6 5-fold axis. And this was done using these conditions. So the self-rotation was calculated in a resolution range between 30 and 8.5 angstrom, and with a Patterson vector between 80 and 400. The diameter of the virus is about 780 angstrom vertex to vertex, and on a grid of 0.75 degree. Now, once we had this orientation, once we knew how was oriented the virus in the unit cell, what we did was looking at the cryo-EM reconstruction of PM2. Usually, EM people has a defined orientation for the icosahedral reconstruction, which is a 2-2-2. So the 2-fold axes are aligned with the X, Y, Z. And what we calculated was the matrix of rotation that would move this orientation in the orientation of our virus. We did that, and once we had the right orientation, once we apply the rotation to our model, then we calculate the self-rotation, and we compare between the experimental self-rotation and the calculated self-rotation. We were happy with the right orientation. Then we moved to the translation search. And this was done always using Explore 3.1 version, which was easy to manipulate in terms of scripts. So once we had the orientation on our EM reconstruction, we prefer to work with atoms rather than with map. So what we did was filling the EM map with a grid of atoms on a 3 angstrom grid, and we start to move in the X and Y plane. Then we found a peak. We were happy, and at that point, we decided to start the real space averaging, and we use a general averaging program, which is a program as in-house program in the David Stewart group. We exploit the full 60-fold averaging because none of the 2-fold axis was aligned with the crystallographic 2-fold axis. Then we moved on solvent flattening, and initially we did just an averaging at 13 angstrom. Then we start to phase extend to 7.5, and this is some partial statistics. Just to give you an idea, we first generate an envelope where we know the virus CT is. Then we mask the central part of the DNA, which has nefast contribution to the averaging, and we average inside this envelope. So we were able to obtain a reasonably good map. This is the packing of the virus. I must say that these spikes, this is a wild-type PM2, this spike I think affect the packing, and they might have affect the lack of high resolution for these crystals. And this is the final PM2 statistics. We use a number of images around 720. This is the completeness. And we couldn't improve more the resolution. So we had to deal and to analyze the structure using this 7 angstrom map. And this is a cut through the virus. You can see the capsid, the spikes. This is the outer leaflet, the inner leaflet. The DNA is masked. And you can see some density crosstalking between the capsid and the outer leaflet. This is the full electron density map. And we focus on the icosahedral symmetric unit, which is here marked in white. These are the icosahedral symmetry axes. Now, the icosahedral symmetric unit is composed by 3 P2 trimers, highlighted here in in this pseudo-hexameric red hexagon. And despite the fact that to us it looked like that it adopts a double jelly roll fold, at 7 angstrom there is no way that you can prove it. So it was a little bit frustrating, but we had to move and to crystallize the protein in isolation, composing the major capsid protein. So we use a divided impera approach. I won't talk about the receptor binding protein P1 that we solved by standard protein crystallography, let's say, and I will focus just on P2 major capsid protein. So the P2 protein was purified from the virus. It was extremely aggregative and is comprehensible if it has to make a lattice for the capsid of the virus. It was the recombinant protein was even worse. We couldn't get CEMET. We could get CEMET, but the crystals were very thin. We couldn't get a normal signal. So we had to work with the native crystals. And although it was very aggregative, the advantage was that as soon as we set up drops, several crystals appeared. But many of them were thin plates or needles. And despite that, we decided to collect one of those thin crystals. Here you have the statistics. It's a very poor statistic for standard protein data processing. You can see an R merge of almost 78. But this was good enough to tell us that we had 2 trimers in the asymmetric unit of when the isolated protein was crystallized. And this was the packing. So we had 2 trimers within the asymmetric unit. There was the threefold, this is a self-rotation for kappa 120, and this is a native Patterson, showing that there is a translation between these 2 trimers. So the point was to get a better crystal, and we tried several things. At the time, we used the PPF optimization screen or the additive screens, and only one condition, with a little bit more sucrose, with 6% sucrose, we were able to obtain a thicker crystal. So we went for it, and we collect data from these new crystals. And this is the kind of diffraction image that we obtain. The resolution is pretty good, 2.5, but we had 2 predominant lattices. So what we did was first indexing one of the lattice, then the second one, and then merging them together. And we got a reasonable quality statistic for this data processing. The CCP4 Weekend is for on molecular replacement, so I won't explain how we did the data indexing and processing, but you can see that we had a high over SIGI overall, and in the last resolution bin, we had a huge redundancy. And with this data, we decided now to phase this X-ray data. And for these, of course, we use molecular replacement techniques. And at the beginning, I used the models that of the double jelly roll major capsid protein available, like the one from PRD1, like the one from the exon. We trimmed off the loop. We used that as individual protein. We used different resolution range. We used different softwares. And none of them was giving us a solution that we were able then to refine. So we had to change our modus operandi. And we fought back, and we realized that the P2 crystal in reality had enough NCS. We had 6-fold NCS symmetry, having 2 trimers in the asymmetric unit. Then the virus map at 7 angstrom had at least 3 independent trimers that we were able to average together. And then from the average density of these independent trimers in the icosahedral symmetric unit, we box out this average trimer map, and we put in a P1 cell with this unit cell dimension. The diameter of the trimer is around 80 angstrom, and we put in a much larger unit cell, back transformed using SFOL, and the resultant structural factors, amplitude, and phases were used and feed in phaser. And the molecular placement in phaser was done between 30 and 7.6 angstrom resolution. Now, if someone asks me what was the TFZ, I don't remember, but what I do remember very clearly was that there was no way that we were able to discriminate the right from wrong except looking at the packing of the 2 trimers. And we were confident of the top solution, of the first solution, that we had the right packing. So what we started to do was trying to bootstrapping the phases from 7.6 to 2.5. So to do that, we use gap, and as soon as we got the phases from phaser, we started to do cycling averaging, so flattening, a phase extension, and nothing worked. The map was still not interpretable. So prior to that, we decided to do NCS refinement. So we tried to refine the NCS operators of these two trimers, and once we did that, then everything clicked in, the cycling averaging worked, the solvent flattening, the phase extension started to work very nicely, and we could see the improvement of the map. And this was done according to this scheme where we first refining gap the NCS, then we calculated envelopes for the trimers, then we did a threefold and twofold averaging, inversion of the density, the F average were combined with the F obs, etc., and going looping along this cycle. And these are the R factors and the real correlation according to the cycle. I don't know if you can see, but this is from 7.6 to 2.8. We have a blimp here in this resolution, which we believe is due to the restraint when the resolution goes from 4.5 to higher resolution for the beta strand. And this is the experimental map that actually we rebuilt by hand in Qt. And indeed, we had a double jelly roll fold, making a trimer, and this was initially refined in RefMac, and then finalized in Buster. And these are the statistics for the refinement of the P2 protein. So what this effort were they useful, all these efforts? And indeed they were, because we were able then to generate a quasi-atomic model of PM2. Here you have the electron density in blue, and then here you have the atomic model. The P2 forms trimers. Each color is an independent trimers in the equicellular symmetric unit, and also we saw the structure of the receptor the receptor binding protein P1. All these then were merged into the team that we were at the time working on about the phylogeny of viruses. So recently also Dave Stewart crystallized and solved the structure of another protein called D13, which fit very nicely with the double jelly roll fold, and it fits in the PRD1 adenoviral clade, which is this one. So this is a phylogenetic tree based on structure. There is no sequence homology. And actually, if you check the sequence homology between these different viral proteins, it's less than 10%. And also, all these efforts have made possible to reveal that viruses or phages that have this fingerprint as a double jelly roll fold have also a common principle in assembling and architecture. Here you have a schematic representation of PM2, of PRD1, of adenovirus. Actually, this is the original image that Roger Burnett published in his Nature paper, and this is of PBC1, which is an alga virus. All of them have a double jelly roll fold capsid protein, and all of them obey a similar architectural principle. And finally, this helps us also to rationalize the virusphere. This is how the virusphere appears today with a classical Baltimore classification, and this is how it would appear if we would use the structural base phylogeny. So, conclusion from lows to highs, and actually this was a journey because we were getting very excited and then very stressed because we couldn't move forward, is that if you have to do some phase combination, then you have between low resolution and high resolution data, where you have to make sure that you have an overlapping in terms of ranges between the low resolution model and the high resolution data. Also, it's extremely important the position of the NCS. This was essential in our case, and I bet is essential in any other case. And as many NCS you have, the better it is. And also the extension, the phase extension is good if it's progressive in minimal steps. And also my piece, a little bit of advice, is that don't give up at the first, or the second, or the third. Keep going, because I think that there's a lot of things to do. Yeah. Also, I want to finally acknowledge the people where I did mostly my work was with Dave Stewart in Oxford. Also, I thank John Grimes, John Dipros, and Bob Esnoff, and also Dennis Buffer, with whom I am still collaborating. And also I want to thank the people in my group right now, which allow me to continue working on viruses. Dani Vadia, he's my postdoc and working on virus structure. Magda Vochita is my PhD student. She's finishing and she's moving to MBL. Pietro Versi, who I stole from pathology for 1 year only, anyway, and is working on a very complex virus receptors. My lab technician, David Gill, who is the EM platform manager in my group, and the funding agency. Also, where it is, the Biogun is in the Basque Country over here, and where is the Guggenheim located. This is, I wish would be our institute, but it's only this one. And just a little bit of publicity. I have vacancies available. One of them is funded. And if some of you is interested, please contact me here on the email or email me. And if you have any question, I am happy to answer them. Thank you.
On his incredible journey. Randy.
I'm just curious, how different was the double jelly roll fold compared to the ones that you couldn't use as molecular replacement models?
Well, if you superimpose them, the RMSD is about 2.3 angstroms, so 1.6, depending which of the double jelly roll you use. The closest to our double jelly roll was the major capsid protein of an archaeal virus, STIV. And even with that one, we couldn't phase it. What we believe is that the angle between the two jelly rolls, even slight movement, might have affected the phasing, because you know that the phase at the border of the ring can change quite a lot if there are small rotation. But the closest is the ones from Steve. And I think it's 1.9 or 1.6 RMSD, the overall. When we started, we just trimmed all the loops because we thought that the core should be conserved. Also, this double jelly roll has alpha helix orthogonal to the direction of the beta strand. And usually that is used to give the angle of these two jelly roll. And those seems pretty conserved. So we believe that small movement between the trimers, between the monomers within the trimers, would that make a trick.
Tom.
You showed a rotation function early on one of your slides where you could see the pentagon.
Yes.
Yeah. And you matched that up. It looked very much like there was another rotation about 3 degrees away. And could you just talk a little bit about that?
We believe that is the twofold crystallographic symmetry. That is the double peaks in each is because you can get from the twofold of the C2 space group.
Any other questions? Thank you very much for. Oh, so you coming back, Tom?
Yeah.
Yeah.
If it was a crystallographic.
No. It was not crystallographic. It was.
Yes. Okay.
Well, thank you to Nicola very much for taking us on the high and low waves of his journey. Our next speaker is going to teach us how to Photoshop our protein model and tell us about totally model-free refinement. We've had reference to Kevin's cats and dogs, but not his ducks so far in this meeting, and we're very glad that he's made it to talk to us today from York.
I need a microphone. Is that okay? Yeah. Right. Okay, so At this point, I would normally thank the organisers for inviting me. Actually, I was coerced into it. I don't know if other developers have this problem. People expect me to come to talk, to be able to talk about anything, and ask me to talk about something I know nothing about. And that was... but Ellie was very persuasive, so I realised there was a piece of research I could dig up and try and bring to something worth showing you. Now, of course, nothing ever goes to timetable, so everything is very preliminary here. So, Photoshop is a verb these days. It refers to altering a photographic image digitally using computer software, typically used to make pictures more attractive. So maybe that's something that we could apply to our proteins as well, and maybe that's useful after a molecular replacement. So here's an example. Now, those of you who are watching the webcast won't be able to see me, and so you will have to guess which is the original and which is the photoshopped version. But one of these is the version which appears on my website. Right. So what comes after molecular replacement? Refinement, which unfortunately often doesn't work because we're too far from a solution and trapped in a local minimum. Now, so one of the things we do is we calculate likelihood-weighted maps, which reduce the noise by down-weighting erroneous phases. But in poor cases, they still show a lot of noise and lower resolution because the higher resolution terms get down-weighted more when your solution is poor. So we can see this in some respects as a low-resolution refinement problem. But low-resolution refinement is hard because of the data parameter ratio. So one of the typical steps to address this is to increase the number of restraints. You either apply restraints on your bond lengths and angles and secondary structure features and anything else you can think of. Or indeed go to a torsion model. The alternative approach is to actually reduce the number of parameters instead. So what we want to look for is very parsimonious parameterizations of the model. And that's the thing I was looking at in this work. There is a second problem that it would be nice to address, and we can do both at the same time. And that's unconventional molecular placement. So, for example, as we've heard, molecular placement using EM density, or, for example, molecular placement to determine NCS operators or cross-crystal averaging operators. In both of these, your search model isn't an atomic model. It's a cut-out piece of electron density, which may have come from EM or from another crystal form in the case of cross-crystal averaging. So, if you've just got electron density, how are you going to refine your result? Well, you can do some rigid body refinement, but after that you tend to be stuck. So, what can we do? So, here's a case. We've got a model. It's got a bit of flexibility. What we'll do, because we've got no atoms, we'll stick some control points on it. These are going to be things that we're going to refine as if they were atoms. And if you've ever photoshopped a picture, then you know you can just click with your mouse and drag a bit of the picture, and it all deforms about the point that you're dragging. So what we're going to do is something very similar with these points. They don't have to be on a regular mesh, but for the general case, that's all you can do. So here's a case where we've got a model which has been distorted. So you can see that we've got a bit of a hinge motion and a bit of twisting going on here. Here's the two superimposed. You can see the differences. So we've got these two closing up. So what happens is what we will do is move the control points in order to drag the density from our known structure to give a better fit to the structure we're trying to solve. So that's what's happened here. We've got the same mesh here. Every point is in the same relative position, but they've all been moved in line with the distortion of the electron density. So, doing this, our model can be as parsimonious as required. We simply change the density of control points. There was one missing piece. I'd had this sitting in the back of my head for best part of 5 years, but I'd never really got excited about it enough about it to do anything about it. I hope in that time it hasn't become obsolete. But the thing that really made me excited about this was the grid search algorithm from Tom Terwilliger's model morphing software, and that was the missing piece to make this something interesting. So what you get then is a two-step calculation. Right. Oh, I see. Can you still hear me? Right. Okay. So the calculation has two steps. For each control point, we'll find the best position to place it in the target map. So on the basis of the density that's around it. So we'll do a little translation search for that density, much as in Tom's morphing program. And then what we're going to do is distort the search density onto the target map using the control point shifts. So let's illustrate that. At this point on the left and its surrounding density, initially we're just using translation searches. It's pretty simple to incorporate small rotations as well. The best match for the density in this map is down here, so it's moved down a bit. And then if we go to this point, then the best match is down here. So you can see there's also been a bit of a rotation here. So we find both that things have moved and how they've rotated by the shifts to the control points. So the second step is to distort the search density, our known density, onto the target map using the control point shifts. So in order to get the density in this grid point with the question mark, I'll look at the surrounding control points and pick the density from the point relative to those points that corresponds. In fact, in practice, we don't just use 3 control points. We use a sphere of control points with a distance-weighted superposition. And in future, there's the potential for some robust statistics there to deal with noisier cases. Right. But of course, if we're doing molecular replacement, we don't usually have phases for the target map. So we've got our search density, and we've just got structure factors for the thing we're doing the molecular replacement with. So we calculate the target map using the observed magnitudes with the phases from the search density in our first crude positioning using sigma A weighting. So that's completely standard. That gives you a model-free refinement method. So we're going to have something called the working map, which is our current best map to go with the structure factors of the structure we're trying to solve. And then our initial working map will be just what comes out of the molecular replacement, putting our search density into the target cell. So we will generate a target map using the observed magnitudes and the working map phases with sigma A weightings. So we do our standard sigma A calculation to get a best map. Then we'll calculate the control point shifts to match the search map onto the target map. So we're now going to refine our search map against our sigma A map. And then we'll distort the search map using the control point shifts to generate a new working map to feed into our next sigma A calculation. So that's the cycle. I'll show you it in pictures. So here's a test case. The red is the structure that we're trying to solve. The blue is the search density. This is from a molecule with 2 domains where I've changed the angle between the domains. And then I've done a best fit superposition so that we've got as much of the molecule aligned as possible, but if you go out to the extremes of the molecule, then the fit is really bad. So we don't know the red density, we've got the blue density and the structure factor magnitudes of the red density. So all we can do is calculate a sigma A map, and it's is this yellow or green? Someone who's not colorblind? Green. Okay, so the green density of the sigma A map, so that's the best map we can calculate. And in other regions where the alignment is better, it looks quite good, but out on this fringe, it's completely rubbish and uninterpretable. So this is a 4 angstrom map. So here's our first working map. So what we do is we fit the working map to the sigma A map and then distort our search map using the resulting shifts. And what comes out is this. It shifts a bit. So then you do it again, it shifts a bit more, and again, and again, and again, and again. And we're refining our electron density without even having a model. Right. And then if you calculate the final sigma A map from that final model after 10 cycles, it looks like that. It's a bit Zeno's paradox. The shifts approach where you're trying to get to but never quite get there. I'm going to look into that long term. There's a look at what happened for sigma A map correlation over the entire calculation. This one started a bit over 50 and has gone up to over 80. There's other things that this can get you. This same method of moving the control points gives you rescaling of the map for free. So in the previous case, when we found heard that lecture before last, where we heard that the unit cell was wrong, it would be able to solve that problem for you. Or also in EM, you don't generally know that the scaling of the map very accurately, how big an angstrom is in your EM image. So the same method will handle that. It just moves all the control points apart slightly. It's not a cure-all for everything. I'll use this, it's simpler. I don't do topology. Right. For now, this only really handles domain-like motions. So, for example, there's something that morph does very well, where we've got one chain which can slide relative to another compared to a homologous model. That wouldn't be handled well by this. That's handled rather nicely by Tom's program. So there's possible ways to deal with that long term, but it's not. It only solves some problems. Right. What can we? I'm even more excited about what we can do with this in future. One of the things we can do is attach a B factor to each control point. Now, you can. What you can certainly do is then refine the B factor as a function of position in the map. And how you do that, you have to have an ensemble of maps which in the most naive case would have different B factors, and you'd interpolate between them to optimize the B factor of the target map with respect to the search map. You can do it a bit more intelligently than that, but that's the basic idea. So then you can refine together NCS copies which have different B factors, and again, you can apply it with EM and such like. So that's interesting. Possibly the most exciting thing, although I don't know if we can do this without a model, is attaching an anisotropic B factor to each control point. So this may require a model. I need to work through the maths to see if it's possible without. And the exciting thing about this, if you have a tetrahedron with the corner points which have anisotropic B values attached to them, and you just linearly interpolate the anisotropic B to any point contained, then that gives you a description which is mathematically identical to a TLS description. And each anisotropic ellipsoid has 6 parameters. Once you eliminate one parameter from each of them for the overall B factor, then you've got 20 parameters total. So it's the same number of parameters as a TLS description. So that's a completely different way of representing TLS. If you just scatter these control points through your structure, then you get TLS, which varies as a function of position in your structure without having to allocate TLS domains at all. So that's an interesting possibility for the future. So that's everything I had to say about that. Just in case you haven't seen it, I'll give you a quick plug for the new RNA and DNA building features in CCP4 and COOT. The new version of CCP4 contains Nautilus, which is just like Buccaneer, except for DNA and RNA. So if you've run Buccaneer, then you can run Nautilus on your nucleotide structures as well. And the other thing we have is the same thing implemented in COOT. This is so incredibly fast that you can do it interactively. Here we've got some base pairs, and what we're going to do is click this button, and it's going to build it for us. And it's that quick. And it's got this bit correct. That was pretty easy. If we scroll over the other way, it's got this bit wrong, so it's not infallible, but the iterated scheme that you get through the CCP4 interface involves RefMac, and that does a better job, but the refinement takes a lot longer. So we've just gone and clicked on another bit and built the second copy, and that's actually overwritten the bit that was wrong because it's found a better interpretation for that density. We can zoom out. We can see we've got helix with a hairpin on the end. And we can have a look around and see what the density's like. This is at about 3.4 angstroms. You can see that bits of it are reasonable, but bits of it down here are very broken. So it's an easier problem in many ways than protein. We certainly couldn't trace a protein chain which looked like this, but we can do it with the nucleotide. Here I get a bit confused because I don't have much experience with nucleotides, but if you turn on all the atoms, then you can see actually it's got it right. It's a kink in the helix. Okay. Right, so I forgot to mention George Sheldrick. George Sheldrick, I can't get through here. So I'll mention this. George Sheldrick mentioned this TLS from anisotropic idea a couple of CCP4 study weekends ago, and he actually tried it using big restraints on the anisotropic coefficients. But I think what it actually needs is the parsimonious parameterization rather than extra restraints. So that has certainly encouraged me to push ahead with that, and Tom Terwilliger's morphing idea was the thing that made the model-free refinement potentially worth pursuing. Funding came from CCP4 and BBSRC.
Do we have questions for Kevin?
Judith Debreceni from AstraZeneca UK. My question is to your model-free refinement, and the question is what sort of R factor or R3 you can assign to such calculations. How do we know that we are on the right track?
So you can calculate R factor or R3 exactly as you would normally, except using your search electron density instead of your coordinate model. Now, if that is from an independent source like EM, then that's completely valid. I expect that the scale's going to turn out. The sort of numbers you get out are going to look rather different depending on the problem. But we don't yet have any experience of using this on real problems. I'll turn it into a real program over the course of this year.
Danny.
Danny Axford, Diamond Light Source. I might have missed it, but how do you decide on the number and spacing of the control points?
At the moment, we don't have a rule for that. So what you can do is make them more finely spaced, but at some point you're going to start needing restraints to have them moving in concert, or you can make them more coarsely spaced and use a bigger sphere around each, which gives you more information, so the motion becomes a bit more stable. The controlling factor is really the radius of the sphere around each point that you are using when matching up when doing the first step, the search for where this control point should move to. And there is my initial experience is that the calculation is a bit sensitive to that. So the example I showed works with a sphere radius of between about 9 and 15 angstroms. If you go outside that range, then it stops working. But that's something that still needs to be explored.
Martin.
So the morph algorithm drags the map around attached to a protein, and therefore has an opportunity to retain stereochemical correctness and probably be conditioned by it. Is there any prospect for including that in your control points, or does that restrict the application of this model-free approach?
Yes, you can. So if you set up a simple mesh of distance restraints, that's actually all you need to constrain local geometry, and then global geometry can change as things flex. What I haven't looked into is, when you're deforming an entire lattice of these things, then something's got to stretch somewhere. So at the moment, I'm not sure if that will cut it or not. But the alternative is just to go to a sufficiently coarse sampling that you don't need the restraints, that there's enough information to keep the thing stable.
Tom Terwilliger, really nice, Kevin. I wonder, as you point out, the radius over which you average, that length scale is quite important. One might imagine that starting off at a big length scale and then progressively making it smaller might work well. Have you tried that out, and does that?
That's a good idea. I'll try it on this test case. Yes.
Hi, Dave Briggs from Manchester, over here. So you didn't maybe implicitly state this, but what are the implications for model-free refinement on bias from a molecular replacement model? Is there any carry-through at all? Is model-free refinement essentially bias-free refinement as well? What is the...
No, the bias still comes through your sigma A map and the limitations of that. So you've still got the problem that your phases are a stronger constraint than your magnitudes. And then you're limited by how much you can make your electron density model fit the electron density and fit the structure factor magnitudes. And again, if you increase the fineness of the sampling, then that's can potentially get better and better unless you restrain them somehow. So I think the bias problems are very similar to existing molecular replacement. We've just got the opportunity to use different sources of information.
Do you have any more questions for Kevin? It remains for me to say two things. First of all, if anyone's been trying to work out the space group of my scarf while I've been standing up here, I'll put you out of your misery and tell you that it's a Dan Sheshman quasi-crystal, and there's no space group. to be told, and to thank our 3 speakers in this session very much, and ask you to come back promptly at 2 o'clock this afternoon.